Hello everyone, welcome to my channel, and in today's session we will be discussing nature of light and electromagnetic radiations. So as per the previous theory that was given by Newton, this is corpuscular theory, the light was considered to have particle-like nature. And this theory was able to explain reflection and refraction concept, but was not able to explain the concept of the interference and diffraction. So because this theory was not able to explain some of the concepts of light, the other theory was given, that is given by Huygens. Huygens theory says, it talks about mainly the wave nature of light. Okay, so initially that wave nature of light was only focused upon light. But later on, by Maxwell, it was found that not only light but even the other forms of the radiant energies, they have wave-like nature. Right, so all the radiations which are emitted, they are having wave-like nature, and they were called as electromagnetic radiations or electromagnetic waves. Okay, now why they are called as electromagnetic waves or electromagnetic radiations? Because they are associated with electric and magnetic field, both perpendicular to each other and also to the direction of wave. For example, if this is the direction of the wave in which the wave is going, and if the pink one which I am writing, this is the direction of electric field, then magnetic field will be still perpendicular to it. That means all three, direction of wave, electric field, magnetic field, all are perpendicular to each other. Right, so that is why these are called as electromagnetic radiations. We can also depict it in this manner. This is the direction of wave, and this is electric field and the magnetic field. So all three are perpendicular to each other. I've just shown it. It's a 3D figure, so it cannot be drawn that way, but otherwise I told you this is the direction of the propagation of the wave, this is electric field and magnetic field. All are perpendicular to each other. So when it is moving in the form of a wave, definitely it will have the wave characteristics also. So what all wave characteristics are possessed will also be there for the electromagnetic radiations. So suppose this is the wave we consider. Every wave will have the upward displacement. This is the upward maximum displacement and the lower maximum displacement. This is upward maximum displacement. This is downward maximum displacement. So the upper part is said to be the crest and the lower part is said to be trough. This is crest and this one is trough. Right? That the upper displacement is said to be the crest, the lower displacement is said to be trough. So crest, trough and wave is always having this nature. Now the first wave characteristic is wavelength. The symbol for wavelength is lambda. We write like this and we read it as LAMDA, lambda. Now it is defined as the distance between two adjacent crests or trough. This is one crest, this is another crest. So between two adjacent crests, what is the distance? That is called as wavelength. It can be even considered two adjacent troughs. Either way it is the same thing. So because it's a distance, it will have all the distance units. It can be represented in angstrom, nanometer, picometer, micrometer, and these are the conversions, children. 1 angstrom is 10 to the power minus 10 meter, which can also be written as 10 to the power minus 8 centimeter, but these are the SI units. Normally we represent that SI unit, so it is this value. 1 nanometer is 10 to the power minus 9 meter, 1 picometer is 10 to the power minus 12 meter, 1 micrometer is 10 to the power minus 6 meter. Got it? This was the first wave characteristic, children. The second wave characteristic is frequency. We write the symbol for frequency as nu. This is the way we write, and it is nu, but we read it as nu. Now what is it? It's defined as number of waves passing through a particular point in 1 second. You take some reference point. Through this particular point, how many complete waves can pass in 1 second? Since we are talking about waves, we are calling frequency as number of waves per second. Otherwise, frequency can be of anything. It can be vibrations per second, okay, cycles per second, but this is waves per second. So its unit is, SI unit is per second, or we can also write hertz. Even you will find this with the short form hertz. Right. The next wave characteristic is velocity. Velocity is defined as a distance traveled by a wave in 1 second. It's normally, how do you define velocity? Distance by time. So distance traveled, because we are talking about wave, we will say distance traveled by wave in 1 second. And its unit is meter per second, SI unit. If it is centimeter, we will write down centimeter per second. Usually all these particles, they move with the velocity of light, so we have written this C. And what is the velocity of light, children? It is 3 into 10 to the power 10 to the power 8. 8 is meter per second. 8 is meter per second. Right? If you are writing the centimeter, it will be 10. 3 into 10 to the power 10 centimeter per second. The next wave characteristic is amplitude. And amplitude we write down as A. Suppose you have a wave like this. So from this mean line, what is this maximum distance? The height of the crest or the depth of the trough? That is called as amplitude. The height of the crest or the depth of the trough, that is amplitude. And amplitude of a wave determines the intensity of the radiation. This is very, very important, children. In MCQs also this can be asked. Amplitude determines intensity or brightness of the radiation. Got it? The next wave characteristic is wave number, and we represent as nu bar. That was frequency symbol nu, and then we write down bar over it, so it's nu bar. And the definition for that is number of waves in 1 centimeter in unit length, or 1 meter. Suppose it's a unit length. In this, how many complete waves are there? How many? One crest, one trough. That is said to be one wave, one wavelength. So number of wavelengths per centimeter, number of waves in unit length, if we are talking in meter, that way we can write. And wave number is 1 by lambda. It is inverse of wavelength. Wave number is inverse of wavelength. So we can write the SI unit as per meter. This is represented in meter. So 1 by meter, per meter. And children, these are some important formulas which you will require for your calculations related to the electromagnetic radiations. That is frequency C by lambda, velocity by wavelength. And since 1 by lambda can be written as nu bar, we can also write it as frequency is equal to C into nu bar, velocity into nu bar. Whatever is given, on that basis you can choose the formula to be applied. Right? Another formula is, in case, sometimes energy is also to be calculated, frequency or wavelength they give. So energy is h nu. If frequency, what is h here, children? H is Planck's constant. H is Planck's constant. And the value for that is 6.626 into 10 to the power minus 34 joule second. If you are writing in ergs, it will be 6.626 into 10 to the power minus 27 ergs a second. Based upon what is given. If you are writing in MKS system, we will be using this, and this if CGS system we are using. H is Planck's constant, and this frequency, whatever frequency is given in the question, we will use it. Sometimes wavelength is given, then in that case we will be using the formula energy is equal to hc by lambda. Now here very important thing is, children, lambda many a times is given in angstrom, nanometer, picometer, micrometer. Never use lambda in those units. You always have to convert it either in meter or in centimeter. If you are using the centimeter, then h value will be this one. If you are using in meter wavelength, then the h value will be the upper one. And usually children, they learn this hc value, the product value. You can put that h value, you can put the velocity of it. So what will you get here is 19.878, I think, into 10 to the power minus 26, because that is 34 and this is 8. So that you subtract. So that product, if you learn, your calculations become little easy. So for that reference only I am saying, not otherwise, right? And at the end, we are also discussing the characteristics of electromagnetic radiation. One characteristic I've already discussed with you, that is they are associated with electric and magnetic field perpendicular to each other and also to the direction of the wave. The second is they always move. Electromagnetic radiations, they always travel with velocity of light. And this is the velocity of light I already told you. They always propagate with the velocity of light. And the last characteristic of electromagnetic radiation is they do not require any medium to propagate. They do not require any medium to propagate in space or in vacuum. They can even propagate in vacuum. That is the reason why we are able to, light on earth. Light reaches us on earth from sun even after passing through the empty space. Okay, so they do not require any medium to propagate. They can even travel in space. That is what I wanted to tell you. Got it, children? So I hope you have followed. This is beneficial.